Hello guys, so welcome again to our vhdl lessons. So in the last recording, we saw or explored the design of the 2-bit binary multiplier using a behavioral model, straightforward design, truth table, 4 Karnaugh maps. You get all the multiplier output here, the product basically of these two numbers, these 2-bit binary numbers. And now it's time to explore another design, which is basically a little bit hierarchical. I mean, you have some behavioral coding, and you're gonna use some of your previous designs as well. Okay, so let's check that. So this is basically the circuit that we're gonna implement. So again, this is exactly the same entity. Also, I just changed the name of the output from C to B. Okay, but this is not a change basically. Again, two binary numbers, each one is 2 bits, and the output we say it should be 4 bits because 3 by 3, the maximum of A and B will give you 9. 9 is 1001. Okay. Now, in this, as we learned in the lecture, this hierarchical design will be something like this. So, in that hierarchical design, we created it based on our understanding of the multiplication operation itself. Okay. And this multiplication operation basically needs these terms here: A0, B0, A0, B1, A1, B0, A1, B1. So in my way of designing this, the first thing I did is that I created these signals. This is basically internal signals upon which we're gonna get our outputs. So for example, B0 is just A0, B0. Look, the ending of A0, B0, this AND gate. Then in our design, we need to have others as we studied that or we learned that. But again, the input of these have others are basically a combination, we can say, of these signals. A0 is B0, A0 B1, A1 B0, A1 B1, and also some other signals that will generate from have others. So for example, half other one has 2 inputs. The first input is A0, B1. The second input is A0, B0. And the output, one of the output is basically the sum. It will be basically B1, the first bit of the product or the output. Okay. And the second output, which is the carry, will be basically the input of the second half other. And the other input is basically A1, B1, this guy here. So what I have done is that I created a signal called AB signal, which means the multiplication, or basically the ending. And the ending in Boolean algebra is just like multiplication and arithmetic, because 0 times 0 is 0, which is basically ending. 0 times 1 is 0. 1 times 0 is 0. This is basically ending. And only 1 times 1 is 1, which is basically AND gate. Okay, so in here, let's see how I could generate AB. AB is basically has 4 bits because we have 4 terms here. So we have 4 terms here: A0, B0, A0, B1, A1, B0, A1, B1. So you can use generate. That's really smart here. You don't do it like this. You can do it, by the way. Something like this. I mean, you can say that A of 0 is equal to A0 and B0. Then A of 1, equal to A1. Of course, I'm sorry, this is A of 0. Okay, and ending with B of 0. Then you just copy this and paste. Copy this 4 times. Then just change, the indices like this, and this will be 2, and so on. You can do that, but you can do something smarter. You can use generate as usual. Usually generate, saves a lot of time for you. Also, you must engineer it professionally. I mean, you should design it professionally, because this may be a source of error as well. Okay. Of course, here we have just 4 combinations. It's not a big deal. But when we deal with, for example, multiplication of 3 bit by 4 bits, no, you will have 11 signals. or 12 signals, yeah, and 11 signals, and you need generate at the time. And if you have higher number of bits for the inputs, for example 8-bit by 8-bit multiplication, definitely you must use generate, otherwise you will be very error prone. So let's now think how to do this generate statement, so it generate what we want. So we want the first bit to be the ending between A0 and B of 0. The second bit will be A of 0 ending with B of 1. Third bit is A of 1 ending with B of 0. Fourth bit is ending of A of 1 and B of 1. Good. So this is the way you generate it. You need to, of course, you need first two counters, one for A and one for B. Okay, because for each bit of A, you're gonna multiply it by all the bit in B. So A of 0 will be multiplied by B of 0 and B of 1, and A of 1 will be multiplied by B of 0 and B of 1. So you need two counters here, I and J. Okay, that's number one. Number two, how to do that in just one sentence, just one line here. So you're gonna do, so the trick is here, this I times 2. Look, 2 here is basically the length of A or B in that case. Okay, the length of A or B. Okay, so let's follow, let's factorize, we can say, or just go step by step for each count, and I will convince you that this is basically will generate exactly what you want. Okay, good. Let's assume first I is 0. Let's write here just like a comment like this. I is 0. Let's check what we're gonna get. So first with J equal to 0. When J equal to 0, so let's check this first. So this will be 0 times 2, which will be 0, plus J is 0. So this is basically will give us A of 0. So in this case, this will give us AB of 0, which is basically that should be that bit. So we are waiting that the result will be A of 0 times or and B of 0. Let's check A of I, which is A of 0, then and B of 0, because J of 0. So that's correct. That's correct. Now let's do 1 when J is equal to 1. Of course, I will omit now all these. And let's check. When J is 1, I am waiting that I am gonna assigning this bit here. So this will be should be AB of 1. We're gonna explore this. And I'm waiting that the ending will be between A of 0 and B of 1. Let's check. Let's again compensate here for I and J. Now J is 1. So I is still 0. So 0 times 2 is 0 plus J. J is 1. So this is basically A of 1, AB of 1. This is exactly what we waiting for. We wanted to assign this bit now, which is bit number 1. Equal to, or assigned to it, is A of I, and I is 0. So this is still 0. That's exactly what we waiting for from A. And the B of J, and J is 1. So this will be basically B of 1. Look, B of 1. So till this moment, we successfully we assigned the first and the second bit, which is bit 0 and bit 1 in EB signal. This signal here, this signal, which is basically 4 bits. 1, 2, 3, 4. These 4 wires are basically the AB signal. Good, AB signal. Now we finished A because I'm sorry, we finished J because J is from 0 to 1. Now we're gonna go back to I. I was 0. Now I will be incrementing to 1. Good. Now we're gonna start again the second loop from 0. Again, I'm gonna remove these. We should now fill this bit, which is basically AB of 2. So let's check. AB of I now is 1. 1 times 2 is 2. Plus J is 0. So 2 plus 0 plus 0, it is 2. So this is basically A of 2. which is exactly what we are waiting for. 2. Okay, now equal to a of I now is 1. Exactly what we are waiting for. b of j, j is 0. So this will give us 0 here. What is this? b0. That's exactly what we were waiting for. Now we finished j equal to 0. We're gonna go to j equal to 1, remove these, and let's check. 1 times 2, because this I is still 1, will give us 2, but now j is 1. So 2 plus 1 is 3, which is basically this bit here. That's exactly what we waiting for. Equal to a of I is 1, so a of 1, exactly what we are waiting for. And b of j is 1, so this will be 1, exactly what we are waiting for. And that's basically how you do it. Okay? So now I think we are convinced now that this, this way of creating the loop or the statement will generate all these signals. This wire A0 B0, this wire A0 B1, this wire A1 B0, this wire which is A1 B1. Now let's check, or create the outputs here. Let's yes, these outputs. So basically, B of 0 is B0 A0, which is basically the first bit in EB signal. So look, B of 0 is equal to AB of 0. Good. Because AB, its first bit, which bit 0, is E0 B0. Now, first half other. So we already have the half other as a package. So I just instantiate, so I included the library here, have other package. I just instantiate a half other here with a label called half other. You can name the label what it's a label. You can name it whatever. So half other, port map, the two inputs. The two inputs is AB of 1, AB of 2. Let's check. We want for this half other, these two inputs, A0 B1, A0 B1, which is basically EB1 of 1. That's right. And for the second input, it should be E1 B0, E1 B0, which is the second, which is bit number 2, AB of 2. That's correct. Now, what are the outputs? Remember, for this package, we create the carry first, then the sum. So the carry is C1. So I generate another signal called C1. Okay. And here it is, the definition of this signal. Then the sum will be basically B of 1. So B of 1. This is our, second output. Now the second half other. The second half other has two inputs again. The first input is C1, which is basically the carry of the first half other. And then the second input is basically E1 B1. What is E1 B1? It is basically the bit number 3 or the fourth bit of AB signal, which is AB of 3. What are the outputs? The output is basically B of 2 and, I'm sorry, look, this is really interesting. And, it's a source of error as well. So look at this. S2, which is a sum, in this package, this package that I create, my package, okay, the second output is the sum, not the first. So the first is the carry, like what I did here, and the second output is the sum. So look, I want B2 to be the sum, so I write it number 2 here. And I want the carry to be B of 3, so I write it number 1. Okay, so this is just an order. This is not, something. This is the way that I created, the designs of the half other. You may make the sum number 1 and the carry number 2. So just follow what you have designed before. Okay, guys. So basically now we have the 4 bits, B of 0, we have B of 1, we have B of 2, and B of 3. Now we just completed the design. Okay. Now let's test bench it. So basically for this test bench, I just used the same test bench that I used for the first design 1, because basically it's the same design. It is the same. Let's look at here. It is basically the same, same box, but I just changing, it changes the internal, structure of this box, the internal design of this box. Okay, so let's check that. So let's open it. Version 2, yes, this one here. Okay, so if you look at here, I just copied and pasted what I have done for the first design, our last lesson. I just changed it V1 to V2. Basically, they have the same name. Okay, just V1 or V2, version 2 or design 2. And also, of course, I changed it C because I called the output C. That's not a problem at all. I just call it B. Okay, because this is basically in the book, so I just used what the book is using. I mean, this design here is basically in the book, so I just used the same design or the same names, we can say. Okay. Of course, I also changed the name of the signal, but again, you don't need to do that because this is basically your choice. This naming are your choice. Okay, but just to be consistent, I just call it B out, and it's good for debugging to know which going to which. Okay, and this is basically exactly what I showed you in the in the previous design. Again, here, what we are doing, we want to test this design for all possible combinations of A and B. Okay, all possible combinations. A can go from 0 to 3, and B can go from also 0 to 3. So we can check 0 times 0, 0 times 1. Let's go to the truth bench test truth table to show it to you in a better way. So look, we want to test when A is equal to 0 with these combinations: 0 times 0, 0 times 1, 0 times 2, 0 times 3. Okay. Then when A become 1, I want to test 1 times 0, 1 times 1, 1 times 2, 1 times 3, and so on. But why to test 1 times 0? Why we already tested 0 times 1? It's exactly the same, 0 times 1. Okay, so here in the for loop, the second for loop, which is basically will assign values to B, I'm starting from I, not from 0. So for A, I start from 0 to 3. But for B, I start from I. Look, when A become 1, I already tested 1 times 0, 0 times 1, basically the same. So I want to test now 1 times 1. 1 times 1. So I will make B to start from 1. Okay, which is basically the same I. Now when A become 2, I already tested 0 times 2 when I was 0. I already tested 1 times 2 when I was 1. So I want to test now starting from 2 times 2. So I will start this from 2, which is basically I. Now for 3, I already tested 0 times 3 in the when I was 3. I already tested 1 times 3. I already tested 2 times 3. So the only thing, or the only combination that I didn't test is 3 times 3. So I will start from 3. Okay, which is basically I now also. So that's basically each time I start from I. Okay, let's compile it. So it's correct. Of course, we didn't change anything, but just in case. Then we simulate. Start simulation. We open this work stuff. It should be multiplier 2-bit version 2. Multiplier 2-bit. Yes, this guy. Okay. So we need to put these down. And change the radix to unsigned to check the output in an easy way, readable way. Okay. Of course, all of them is readable, either binary or, but of course, it will be easier for us to understand if it is, in decimal. Okay, let's check now. Here are all the cases. 0 times 0 is 0. 0 times 1 is 0. Let's change the color here to yellow, for example, to make it easy to see. Yeah. Again, 0 times 0 is 0. 0 times 1 is 0. 0 times 2 is 0. 0 times 3 is 0. 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 2 times 2 is 4, 2 times 3 is 6, 3 times 3 is 9. Okay. I just want to highlight something here. We just finished an error that I did myself. Okay. And you guys may also do, which is basically what I mentioned in here. I switched the carry and the sum. You must remember, follow what you have done. In my design of the half adder, I called the first output carry, the second output is the sum. Okay, so, and in our design here, B2 is a sum, B3 is a carry. And in my design of the half adder, the carry was defined prior to the sum. So I want B2 to be the sum, so I'm gonna write it at last here. And I want B3 to be the carry, so I write it before last. Okay. When I switched them, intentionally, of course, this gives me, of course, incorrect result. Okay. But it was not, so difficult to find the problem, but it may, for bigger design, become a problem for you. Okay. That's all, guys, for this design. Thank you very much for watching this video, and see you in the next video. Bye-bye.